Stand on this side?
Yeah, I'm going to stand over here and point up like this. That's my plan.
Okay, so the last speaker.
Last speaker.
Is David Mandrus. Very fitting because he was also at our very first.
Yeah, I've been to almost. Yeah, I think I've only missed like 2.
Yeah, Dave is going to be the first speaker on, what most of you are probably interested in these days, which is using computers to do things that you don't need to do anymore yourself, right?
Yes and no. Yes and no.
Okay, thank you, Dave.
All right, thanks, JP. Yeah, it's always great to be here. This is a nice community building activity, and it's always great to be with the next generation of synthesis investigators. And so this is the title of my talk. Originally, when I gave this title to JP, he said, "Are you becoming a theorist?" And I said, "No." And so one of my goals in this talk is to convince everybody that they should all be using these LIPs in their research. And they're really easy to use, and they're extremely powerful, and everybody who makes materials should be using these. So that's the goal. All right, so another community building activity is this topical group that we formed about a year ago at the APS. It's called the Group for Quantum Material Synthesis. It's one of the top, it's a GQMS, you can join it. And we have our own invited sessions, we have our own focus sessions, we have our own, we can nominate APS fellows. So I encourage everybody to join and get involved. It's not very big yet. I'm not sure how big it'll grow, but it's a great chance to get involved with the APS. And I wanted to bring some attention to that. Okay, so when I was a postdoc a long time ago, somebody had stuck this sign up. This was at Los Alamos. So a month in the lab can often save an hour in the library. And so nowadays, we don't go to the library much anymore. But we do spend time on the computer. So, and this is the spirit of this talk. All right, so Julia showed the materials pyramid. I think this is a great thing for all young synthesis investigators to get to know. So actually it was at this meeting, this was at Ames, Iowa in 2003 that I first met Julia, actually. And this materials pyramid was created by Brian Sales. He said he created it because he was getting hungry and he was thinking about food, and so the food pyramid and materials pyramid. And so now, of course, we've flipped this upside down. Exactly. But the goal of what we're trying to do as sort of synthesis investigators and physicists and chemists is sort of move materials from the bottom of the pyramid to the top of the pyramid. And there was some discussion of the difference between chemists and physicists. And the way I see it is chemists are mostly working toward the bottom of the pyramid and physicists are mostly working at the top. So synthesis people are here, and then measurement people are more up here. And so obviously the base of the pyramid is sort of the number of materials, and the height of the pyramid. When you get to the top, you learn more and more about the materials. So heavily studied materials are at the top. Materials where we might know the crystal structure, that they exist, are at the bottom, but we don't know the properties. So what we want to do is move them up through the pyramid as fast as possible. That's the general idea. All right, so let me go back in time to about 30 years ago. We were pretty much on our own. We didn't get a lot of help from theory. Nobody was telling us anything. We were kind of left alone. And we mostly proceeded by chemical intuition, structure, property, relationship sort of heuristics, copper, oxygen, planes, things like that. And that worked pretty well for the most part. And but about 15 years ago, DFT became pretty much a commodity. Lots of people were doing it. And so we got a lot of suggestions for materials, right? Like, DFT says, let's make this material. Let's make that material. And it turned out that most of the advice we got was bad advice. The materials just weren't growable. They weren't synthesizable. And the problem is that most of these DFT predicted compounds, even though they had, a formation energy compared to the elements that was negative, they weren't thermodynamically stable. And finally, I stuck the materials pyramid into this report. I was one of the co-organizers. And so this was a big synthesis science. Nothing ever came of this, by the way, but this was a big meeting we had in Washington in 2016. And this was before machine learning was a big deal. And we concluded that exploratory synthesis will continue to provide the overwhelming majority of new materials for years and perhaps decades to come. So that's all the preliminary stuff. And then about maybe in 2024 or so, big tech companies started designing materials. I was saying, geez, what's going on? We have Google designing materials. They're doing our job, right? We have Google. Microsoft was designing materials. Meta was designing, this is Facebook, was designing materials. Okay, so that's kind of weird. And so at first I thought, okay, they predicted a whole bunch of new materials, so what they've done is expanded the base of the materials pyramid. Okay, they gave us a lot more at the base, so that's not really helping us, drive things to the top. And then a few months ago, I got a week where I basically had no meetings, and nobody was bothering me or asking me to do anything, and so I was able to actually I said, okay, let me sit down. Let me try to figure out what Google, Microsoft, and Meta have actually done. And so I started digging into it a little bit. And what they have done is pretty amazing, actually. It's extremely useful for us. And I didn't realize this until I dug into it a little bit. And so the central question is that if you have a composition, will it form a stable crystalline solid, or will it decompose into other phases? Okay? And what you need to answer that question is something called the convex hull. Okay? And so essentially, basically what you want is the stability. A phase is stable if its Gibbs energy is lower than any other phase or mixture of phases at the same composition. Okay? And so basically we're always working at 0 temperature. And so essentially we want just the total energy. Okay? And so what the DFT will predict is like the formation energy. Delta E is less than 0, but it doesn't guarantee stability. A compound must be stable against decomposition into other compounds, not just elements. Okay? And that's where the convex hull comes in. What the convex hull does is it basically checks stability against all other possible decomposition reactions. Okay? And so the convex hull is a mathematical term, and it's the smallest convex set containing all points. It's basically the circle you can draw around these stable compounds, essentially. And so you plot delta E versus composition and find the lower convex hull, the minimum energy surface. And Materials Project will do this. And DFT can do this, but it's very, very expensive, right? It takes forever to do it with DFT. Okay? And so with the convex hull, so you can find the convex hull on Materials Project. And what it does, if you're above the convex hull, it means that this phase will decompose into these two phases. And there's even a lever rule, like your regular phase diagrams. Okay, so if you're on the hull, the material is thermodynamically stable. And if you're above the hull, it's unstable. So it gives you information about how stable the phase is. All right.
Can I ask a question?
Sure.
The phases on the hull, are they always known phases, or are they? I mean, is that part of the?
No, they're not always known. This is what we're getting to. We're going to be able to predict whether an unknown phase is on the hull or not. And we can do it really quickly and easily. That's what they've accomplished. That's what those tech companies have accomplished for us. It's amazing. All right, so convex hull can be calculated with DFT, but it's time consuming and computationally expensive. So using these MLIPs, it is now possible to calculate a convex hull in a minute or two on a laptop. Seriously, a minute or two on a laptop, we can do this. Whereas a few years ago, it took an enormous number, so many DFT calculations that the DFT people didn't want to do it. So this is a huge thing, it's a huge benefit for us. All right, so here's our material simulation. So DFT is high accuracy, but it goes as the sort of the number of electrons cubes, limited scale. So these force fields are basically sort of, these are functions that are you write them in by hand. This is what like molecular dynamics people do when they come up with these. It's like a Leonard-Jones potential, but it's more complicated, essentially. And so what these MLIPs do is they essentially have, they've taken machine learning on all these DFT calculations, and they've come up with these, a neural network that gives you essentially the total energy very quickly. And so they come up with this descriptor vector, which encodes the local chemical environment, and they put it in a machine learning model. And so essentially with these MLIPs you can calculate a few things like the phonons, thermal conductivity, thermal expansion, melting points, elastic constants. But what we're interested in here is this convex hull stability. All right, so the MLIP replaces the handcrafted analytic form with a flexible machine learning model. They did it from DFT. They took hundreds of thousands or millions of DFT calculations. So they ran DFT on tons of structures and they fit it to a model. And so what you get is near DFT accuracy for energies and forces. So you can relax crystal structures, you can get lattice parameters, you know, atomic positions, all kinds of stuff. All right, on Materials Project, there's even this page called MatBench Discovery that benchmarks the various models that these companies have come up with. And so about a year ago, you had Meta's model, Microsoft's model, and Google's model were all in the top 4. And this was really, now some of these have dropped out. Some of them, some of the ones I'll talk about aren't even benchmarked yet. Okay, so this was a benchmark that came out in August in this paper here. And so the model that we're going to talk about today is this one right here. S is for small. So the medium model is here, but the small one does almost as well. The medium model, I'm not sure, I haven't tried to run it on a laptop, but I don't think it'll run on a laptop. I think you need at least a PC with a pretty serious graphics card to run that one. But everybody in the audience can run this one on their laptop, and it's really quick and easy. And the rest of the talk, I'm going to try to explain how to get it going. And we could even, if students want to get it going while I'm here, I'm happy to help in any way I can. Question? Yeah. Yes?
It may be not necessary to actually, why is it called small and different mediums? Is it the size of the database?
Yeah, it's how many parameters are in that machine learning model.
You're saying that the small one is good enough?
The small one is good enough. I mean, they've kind of benchmarked it here. This F1 is a performance in a materials discovery task. And it's almost as good as the medium. You can run the medium. I'm pretty sure you can get it to run on a pretty good GPU. I haven't fooled. I had a week to do all this. This was a week in October I had where people left me alone. Well, no, professors, they never get left alone. They're always being bothered to do something or other for somebody. Some secretary wants this, or you got to, I mean, it's just, Jeff understands. I'm getting there too, Jeff. All right. Okay, where was I? Yeah, small can run quicker and easier with less memory, less. Yeah, it's. Okay, so I put all the codes that I'm going to talk about into this GitHub site, and you can download them and try to run them yourselves this afternoon if you want. It's not that hard. One thing you got to do is, so these machine learning models are on a site called Hugging Face, which sort of, I guess, aggregates various machine learning. It's like a headquarters for the machine learning community. So Meta put all their stuff on there, but you have to agree to their licensing. And there's no problem for academics. Academic use is part. So you put you sign up on here, and about an hour later you get permission to use the models, something like that. You have to create this account on Hugging Face and ask for permission for the model. So you need an API key from the materials project. Probably most people already have this. That's how, if you want to download CIF files, you've got to register with the materials project. That's part of codes. So you have to know a little bit about Python. You need to know how to create a Python environment and install packages. The main thing is getting PyTorch to run on your computer. So you need PyTorch to run this model. The model can run on a CPU or on an NVIDIA GPU. So here are the programs that are in that GitHub site. So this one, download CIFs for phase diagram. So you put in 2 elements, and it downloads all the CIF files from the materials project containing those elements. Batch relax to CSV. It relaxes the cell and calculates the ground state energy for all the CIF files. So this takes, the example I'm going to show is cobalt antimony. I have a Mac with an M4 chip, which is pretty fast, but it takes, I don't know, a minute or 2 to do this. Make phase diagram from CSV. This calculates the convex hull. And then there's this one, replace element in CIF. It lets you replace an element in a CIF file. I'll show an example of that later. And then there's this little graphical user interface that lets you put in like paths and everything, makes it easy to call. Because all these programs have arguments, and rather than typing them in, you can just put them into this graphical user interface. Okay, so here's a sanity check. You can calculate a known convex hull. And so this is cobalt antimony. So what you can see is, so this was the one from the materials project. This was the one created from those codes, basically the same even. So you can see this one, this is cobalt antimony 2. So these are slightly above the convex hull, right? So these are like a few millivolts above the convex hull. But they're still synthesizable. So, okay, so here's an example of a DFT predicted material. I don't want to pick on these guys, but they did get their 300 citations out of this article, so I don't feel too bad. So in 2015, we worked on a material called chromium silicon tellurium-3. We were trying to find 2D magnets even before anybody figured out how to characterize them. We knew this was going to be a thing. So we worked on chromium silicon tellurium-3. I actually gave a talk at a CFAR meeting. I got Jagoon Park interested. Do you remember that one? I think you were there. And Travis Williams worked on this for, he did a lot of nice neutron work on it, actually. And so some of the DFT guys at Oak Ridge predicted this one, right? Chromium tin tellurium-3. And they did careful DFT work, and it said we studied the mechanical and dynamical stability, they calculated elastic constants and phonon spectrum, mechanically and dynamically stable. But when you calculate the convex hull, what you find out is that this compound is 90 millivolts above the hull. Okay, so we wasted, I don't know, a month trying to make this stuff, and it's just not synthesizable. Okay? So here's an example of where 5 minutes on a computer would have saved us a month in the lab. Okay? So.
Is this a ternary convex hull, or is it?
Yes, it is. It is. It's a ternary convex hull. You can plot it, but I don't get a lot of. I just, for this case, you can just say, okay, it's easier just to read the Excel file. But yeah, you can plot it. Okay, so that's one example of where this can save you time.
Can you remind me, so materials project CIF files are for all predicted and known materials, or?
Yes, predicted and known. A lot of those CIF files for materials projects are not on the hull. They're unstable, but they're still in there. I don't know why they're in there, but they are. But yeah, there's.
But also, so if you take this example, all known chromium, tin, tellurium,
yes,
compounds are
all known. Everything in the material. This is all the everything from ICSD, everything that's been reported. Even I think there's a lot of theoretically predicted materials that are in there. Everything that is known about these are in the materials project. You download them, and you can just calculate the stability of all of them, see if they're on the hull or off the hull in like a minute. I mean, it's really fast. And just 2 or 3 years ago, you couldn't do this. Question?
Yep. For this type of calculation, you're presupposing a crystal structure, right?
Yes.
It's not telling you whether anything of that composition might be stable, but only that this.
That's correct.
This.
Yeah, you have to put in a crystal structure. And that's a lot of what they've done is they've cycled. That's how they've predicted millions of materials, right there. But yeah, generally, yeah, this is you have to have an idea of the crystal structure, and a lot of times you do. At least we're often doping, we're doing other things. We're replacing one element with another, and we do have an idea of the crystal structure. Yeah, but if you don't know the crystal structure, it doesn't help.
But I guess that's also where DFT would tell you, is this crystal structure stable?
Yes, DFT will tell you whether, if it converges, right? If it converges and it gives you stable phonons and so forth, or real phonons, not imaginary phonons, I guess is what they look for. Okay, so there's a little bit of a gray area. If it's just a little bit off the hull, it still might be synthesizable. So there's some general rules of thumb. Like if it's a few millivolts above the hull, and these calculations are only good to like 10 or 20 millivolts or something like that. This is a slide that Notebook LM made for me. So according to this paper here, so the median energy above the hull for metastable compounds is about 15. So half of them are below 15 or half of them are above. The 90th percentile is about 67. Predictions above this threshold have a sharply decreasing probability of success. Okay? All right. Yeah, so here's two metastable. This is cobalt antimony 2. These were both in materials project. They're both a few millivolts above the hull, but these are still synthesizable compounds. So if you do your calculation and it's like 20 millivolts above, it still may be worth trying to make the material. All right, so here's another example. This one has been in the news lately. We found it the old-fashioned way just by trying it. But we could have, if this were available when we did this. So here was a phase. So we were working on 166 materials. This phase had not been reported. And so if you go in and you calculate the convex hull, it tells you it's on the hull. And so it has an excellent chance of working. Right? And so here's one, lanthanum, vanadium 6, tin 6. Nobody had reported it. you calculate it, it's about 24 millivolts above the hell. This is probably why nobody's reported it. It's probably not makeable. But this tells you a lot, right? So finally, conclusions. A month in the lab can save you a few minutes on the computer to update our... So after I was starting to work on doping, and then everybody started bothering me again, and so I never got to finish the doping, but it would be great if one of the students in the audience could work on the doping, somebody who, who wants to do this. It's not that hard. I mean, but doping is a little tricky because what you have to do is create a supercell and then put the dopants in different places on the supercell. And then some of those locations have lower energies than others, and then you have to perform some thermodynamic average. So it's a little involved. I've done a little bit, but I didn't get very far, so I didn't want to talk about it.
So just remind me, the input you need is a CIF file.
You need a CIF file.
So you can create so what if you you wanted to do doping, but let's say you needed to make a big supercell, to put one atom out of 10 or something.
Right.
As a dopant.
Yeah.
You can create that and put it in, and there's no problem. It doesn't cost a lot more.
No. It works fine. It works fine. Yeah, just that the number of, if you wanted to calculate every possible position for the dopant, it rapidly increases the number of CIF files that you have to process. And there's ways of dealing with this, and I haven't dug into those enough. DFT
it's not like DFT where if you double the unit cell, then... No. It's everything. It might take 5 minutes instead of 1 minute. It's really doable, and just somebody who it's not that hard. It's somebody who can spend a week or two doing it without emails pouring in, committee work, and what.
Does it give you a hint about how to grow, for example, single crystal versus polycrystal? Or?
It might. I haven't thought about that, to be honest. I think there's a lot here, and I think this goes to what Alana was talking about. With entropy, you might even be able to put configurational entropy into these calculations. I haven't thought about that. I saw her talk yesterday, and I said, you might be able to add this in. I mean, there's examples where, if you have a disordered material, that can actually bring you down to the hull from the entropic term at the temperature you're using, right? So you might be able to calculate these hulls at some finite temperature. I think it's doable, but it takes time and somebody to think about it. But again, if any of the students in the audience want to try to get this going, I'm here all day. I'm here tomorrow too if you want to help, and I'm happy to respond to emails as well. But I'd love somebody, especially the students. Professors don't have time for this stuff. But yeah, a student could work on this. It's not too hard. It'd be really useful for the community. Okay, I'm done.
So I just realized you're now giving the students the ammunition. Your supervisor and say, go and make this material. Now they can come back and say, it's not going to work.
It's not on the hull, yeah. Yeah, no, but I'm really excited about this. It's a new tool in our arsenal, and this is a gift from the high-tech companies, I just assumed that it would all this stuff would take supercomputers to do it all, but once I dug into it, I realized, look, this is easy. This is easy, and all that stuff, all those codes were Vibe coded. It was all written by Claude 4.0 Opus in about 2 days. I mean, it's pretty amazing, right? Some of these tools, but it's really useful for us.
So let me ask the first question. Google and so on, these big projects to predict new materials, have they already implemented this? Like, in other words,
no,
is there a database you can go and see if they already determined whether the materials are, or did they just predict materials?
I think there is a database somewhere, but I haven't fooled around with their databases. I know they're working with the Materials Project to incorporate a lot of this into the Materials Project. I don't know where that stands. And I think
it's so easy, it sounds like it should just be,
They should just apply it to whatever huge list of materials they have, right?
I think they may have, yeah. I mean, this is all doable, but yeah, this allows us to have our own ideas and try stuff.
Yeah. So Atlanta, then Bruce.
Yeah, thanks so much. This is great. I just wanted to add that the part of my talk yesterday that I ran out of time to give was about how we're applying MLIPs to predicting new high entropy oxides, and it actually works great.
Oh, you've been doing it already. Fantastic.
It's
Okay.
great. It's such a combinatorial problem. Like if you narrow yourself down to 10 elements and you want to try all combinations of 4 or 5, that would be easily a full PhD experimentally, and it's like a day. And it tells you just, which ones are the ones worth the effort and the materials going into the lab and actually giving it a try at, or which ones should you put more effort into. So yeah, I think it's a great approach.
Absolutely. No, I was really excited. I don't get excited that often anymore, but that got me excited.
Bruce?
Thanks very much, Dave. It's very interesting. So I was going to ask if there's an example of a success story of a topical material being discovered or being introduced to a given field with these sorts of techniques. Because in my own experience, I realize this is all new, but in my own experience, the really topical problems with kind of launch fields from materials discovery, they use the old-fashioned method, right, where there's a lot of serendipity and a lot of hard work and such. And is there an example where this has worked out?
I don't know. I don't know if there's an example. I don't think this is going to help you find the next interesting superconductor, which we're all waiting for. What it will do is basically save time in the lab. Ultimately, our main resource is time. Right? We don't have enough time. And we don't want to waste time in the lab trying to make materials that can't be synthesized. So that all this really does is save time in the lab. I don't think it's going to help us necessarily find a new superconductor. I don't think it's replacing chemical intuition or physical intuition in that respect. Really, all it's doing is saving time.
There are still a lot of variables, though, that you can just try to optimize. Like, if you really want to grow something, you can...
Right. It helps you understand what you're up against. And there's strategies for making metastable materials. And I think we're really just at the beginning of using these experimentally. And I think there's really a disconnect, right? These teams at Google and so forth, they're mainly computer scientists, right? And they're sitting in their offices and they're doing whatever they do. And they're not talking to the people in the lab. And so that's why I was so excited to find that we could actually run this model on a laptop, right? And it didn't require a supercomputer. It didn't require a PhD in computer science to run it. It's actually pretty easy. So.
Yes.
Thank you so much. This is quite exciting. I was just wondering if the model that you're talking about, that you showed on GitHub, has the capability to accommodate for some extra conditions for synthesis, such as electron transfer or anything like that, or in case we want to model something similar, the best course of action is to download the lips and forget how
Is it MLIP? Is that how you pronounce it?
I think it's MLIP. That's what we've been saying at UBC.
Oh.
Okay, MLIP. Okay, I don't, I've never heard anybody say it before.
I don't know. Those things where I'm in a bubble, so that's what we say. But
Okay. I mean, we can decide right here how it should be pronounced, and then we can enforce our decision. We could call it MLIP. Let's call it MLIP. That's fine.
Sounds better than balloon.
I think it does, actually. There's less chance for a slip of the tongue.
or if we should download the lip or lip, whatever you want to call it, then upload it or import it into whatever software of choice we would have for mechanics or MD or whatever we normally use.
So I can
repeat the first part of the question, sorry.
Okay.
So I was wondering if the model you showed on GitHub can accommodate for some extra conditions that we might want to replicate for synthesis, such as electron transfer being required to form the compound,
Yeah, but how would you, all this does is calculate energies.
So it's like a geometry optimization, pretty much. Then.
It can relax a unit cell, it can relax a unit cell, it can calculate energies and forces on atoms.
Okay.
As far as I know, that's basically what you can do with it. It does it very fast.
So does it assume room temperature and pressure then?
No, it's zero temperature.
So it's like in a vacuum, pretty much.
It's like in a vacuum. It has its limitations.
Got it. It's still good starting tool. I was just
But yeah, I mean, it's just it's a helpful tool that can save us time. That's really what it is. And I think we all should be using it.
Nick had yeah. So I was just trying to think here, again, limitations of what the end does, or we don't need everything that the calculations are getting back to. So, I mean, basically, given some structure, this thing is just looking at either atomic potential so quickly and saying, okay, it's happening.
Right.
So, we have error bars essentially on how well the GMT calculations work in the first place. Maybe this is already good. But I'm trying to think of edge cases. Where are you going to get false positives or potentially miss something?
Yeah, I think so. I mean,
That's
I think your error bars are maybe 10 or 15 electron volts per atom. There's a gray area there. But if you're, like that one example where you're 90 millivolts off the hull, I mean, you can say, look, this is probably not going to work. Whereas if you're, 10 millivolts off the hull, you can say, yeah, it might not work, but it's worth a try.
Well, I mean, my argument would be 10 millivolts is already covered in the error bar.
Yeah, no, it's,
90 is too.
I think 90 is beyond the error bar, but again, you're welcome to try. You're welcome to try to.
I don't think you think about this energy as like what you would think from an electronic band structure or in phonons, I guess.
Yeah, no, I think
This
it's.
is a different.
Yeah, it's really good at finding these energies, and you can compare it against the DFT, the benchmark DFTs, and you can calculate your own convex hull and compare it to Materials Project, and it does pretty well. The one area it may not do as well is like with F electron materials, with lots of F electrons. I don't know how well it does there. Those are a little trickier, but I think it probably does okay.
Frank and then
Thank you for the wonderful talk and also for putting the code together. So with how do you get the CIF files? I guess there's like all sorts of stuff on material about it, but so I guess we're stuck to just choosing one of these things.
Yeah, so there's a Python package called PyMatGen that was created by the Materials Project. It stands for Python Materials Genome. That was all started with Materials Genome Project. And it allows you to just put in it allows you to download CIF files from Materials Project very quickly.
But there's no, I guess there's no way to say, given this type of structure, might be using, or maybe that's.
Yeah, there's probably, there's stuff out there like that. I mean, Daniel Shoemaker he has a program where you can put in like different kinds of lattices and it'll try to find materials with those lattices. If you want to find Kagome lattices, it'll try to find Kagome systems, things like that. That's doable. That's a little harder, I think. I mean, this is all really elementary, simple stuff. But yeah.
so in principle, this previous to this kind of approach, if you wanted to say you want to make a boron Kagame lattice or something, I would do DFT to see if it's stable, and then think about energetics and things like that.
Right.
That's computer intensive. Now you're saying I could just generate a CIF file with whatever software I want, or just write the text file, put it into this, and it'll
It'll tell you
if it's stable.
if it's stable or not. Yeah. Yeah. No, you don't.
Regardless of whether DFT tells
I mean,
you.
we've all fiddled around with DFT codes, and they're fiddly, right? It's you know, getting things to converge and all these different parameters and everything. I really don't enjoy that very much. There's none of that with this. It's plug and go.
But it's only telling you, relative to what other phases are.
Right. No, it tells you.
If you have a uranium compound or rare earth compound with F electrons,
we can, again, we don't.
it's going to compare to whatever's known.
It's going to compare to what's known, and I mean, they've compressed all this knowledge into this machine, this graph neural network that you can run.
Okay, there was Keenan and then two people over here. Keenan.
The answer is probably no, but I'm just wondering how this would handle situations where a system might only be stable, up to 100 nanometers thickness, thin film. No? All right.
I don't think so. You might be able to figure out a way to make it do that. I don't know. I mean, it's not a silver bullet for everything. All it does is help us decide how to spend our time in the lab.
Okay, I don't know who was first, Melanie and...
I just wanted to comment on what Dr. Zhang said. I think there's this program by Argonne National Lab called Dioptas, and I've only done it one time, so I'm not entirely sure, but I can change the composition of one of the atoms in your zip file, and then you have a new zip file that may be used for this. I'm not
Yeah.
Does it have to be changed to color?
There's a package called ASE, Atomic Simulation Environment, that has all kinds of like utilities for handling CIF files.
Yeah, if your question was how to generate a zip file or just manipulate it?
That's like stable.
Oh, that's stable. Well, no, I mean, that's what DFT would do, but you're saying that
Yeah, no,
this is a maybe shortcut.
DFT I think is still the gold standard, but it's not something, we're not going to sit down and do 50 DFT calculations before we get in the lab.
I mean, it's true that DFT is going to tell you if the atoms fly apart or not, whether it's stable to put them in that bonding configuration. Which isn't always going to be correct, but at least tells you that. And especially if you consider it based on just the forces of the atoms, like use fast. It's pretty quick to do that. It's not too hard to do.
Julia.
But beyond that, then, yeah, the energetics is correct. So there's another student here, and then Julia.
Yeah, so I just want to make sure I understand how these models are generated. Is it generated from DFT and knowledge structures?
It's trained on millions of DFT calculations.
Okay, so then I would wonder if there is actually transferability for similar structures. Like if you want to do doping, you might create a supercell, right?
Right.
But those are not input in the training set, right? Say if you just use identical structure, create a super lattice without doing any doping, you'll still be able to predict it will be a stable or it should still be reliable.
I think it will because it looks at the local environment of each atom.
Okay, so it's transferable.
I believe it is, yeah. I believe it's quite transferable. Again, I mean, I didn't create these models. I just realized that you could run them on a laptop. That's really all I've done.
Okay, Julia, and then Nikhil.
Yeah, I just want to make a comment. I would always subscribe to the fact that shows any local reference.
Could you talk?
Can you speak up a little bit? Sorry.
She says you have to use ICSD first.
And check the references. Right, check the original reference. It's not complicated. It calculates things. ICSD reference. Check that there's actually a shortcut determination. And that would be
Yeah. No, I think most of the ICSD data has actually been imported into Materials Project, and it'll tell you which ones are experimentally validated, and it gives you the reference. But I agree. I mean, it's always good to use real data rather than simulated data.
Yeah, no, I mean,
Thank you. I was just wondering if those libs have good coverage for most elements, or if based on the search you did on the 1 week they left you alone, you would say that there's limited coverage because, of course, like the training data set comes from DFT data that's out there. So some elements might not be as used as often. So I guess what I'm asking is if you think that the error is higher for some elements as opposed to others.
yeah, I would guess that things like transuranics are not going to be as reliable as, iron or something.
Yeah, I also wonder about like hydrides, for instance, where
Lanthanum
H10 is that
exactly.
way off?
We should try it. I mean, but
I'm sure that's
no, I mean, yeah, this again, there's going to be weaknesses like everywhere else. There's probably gaps in the training data where the things are not going to be as reliable. You just have to sort of try to realize the limitations of what this can do.
Yeah, actually, I wanted to make a comment, and it's exactly related to this. So, one of the weaknesses that we've encountered quite often is that if you start from an unphysical assumption, often you'll find it's stable. And that's because the DFT, the training data set didn't contain configurations that looked like that. So if we make really weird assumptions about oxidation states, like if we say, okay, this calcium atom is going to have a 4+ oxidation state, that doesn't exist in the DFT training data. And so it's like, yeah, it looks fine. But we know that that is never going to happen, that that's completely unphysical. So you have to start with a physical assumption, or else you might find something really strange.
Yeah,
so this is why I think you still need people who understand something about materials to be.
Oh yeah, no, this is, yeah. Again, I see this as just something to save people time in the lab.
Yeah.
We're not trying to eliminate the scientists. Although there are people who are trying to eliminate science. But that's not me. There's this new company called Periodic Labs, right? And the first thing they say, we are trying to create an AI scientist.
Any other final thoughts or comments, questions, answers? Oh, yeah.
I just got a question about clarification we're asking. You're more kind of talking about using more as kind of now this envelope calculation where it's just a way to quickly see does this look like something that we can actually be working with, or is this something that maybe I should look elsewhere first and then come back?
Yeah, I caught about half of it. I'm sorry.
Basically, the use case scenario that you're describing here is less as kind of like you said, it's not the golden rule. The golden rule would be DFT. You're saying use this more like how you would an envelope calculation.
Yeah. No, the use case here is okay. I have an idea for a material. What is it likely that I can make it? And if your idea, you create a CIF file, you put it in, you compare it on calculate a convex hull. If it's way off the hull, let's try something else. If it's on the hull, you say, yeah, it's probably going to work. Or if you want to have an idea to dope a material, you can try to dope it. Yes, this will probably go in and give us a reasonable, chance of working. It's just really just think about it as a way to save time and get results quicker. We're not trying to go off in theory land somewhere. It's really practical. And it's not trying to get you out of, it's trying to allow you to just spend your time in the lab more effectively. That's all.
I would say just think about AI, if you want to generate a fake picture of something, it pixelates and does, you say make a picture of Jeff doing a neutron scattering experiment on the moon. It will, doesn't know, okay, I have to do this, just, interpolates essentially.
Yeah,
Think of it like that. It's just taking all this sort of hard work of DFT and then interpolating it in all the results. So, you probably will do a good job. Jeff on the moon, I don't know. Okay.
Actually, we'll have to generate one of those.
Okay, so thanks, Dave.
All right, sure. I really hope at least 1 or 2 students can get this working by the end of the workshop. I mean, it literally can be done in a few minutes. Well, a couple of hours, I say, not a few minutes, but because you need to wait for permission, right? It's going to take an hour at least to get permission to use those models.
And if someone creates a nice GUI package, then you can share it with us.
Yeah. Please share with the community. If you do something with this, this is really valuable for the community.
Okay, so we have a coffee break, and then at 11 o'clock we'll come back.